Thank you everybody so much for coming and joining with me. We're going to spend a wonderful 45 minutes or so together to talk about this language, which I hope will have lessons for everybody. So I don't want to give just another talk about Rust. There have been plenty of those on the internet and in person. What I think I would like to really share is both why Rust is becoming more and more significant as a programming language for the entire industry worldwide, and also maybe a few lessons for any programming language. So 2022 was a long time ago. If anyone can think back, I was on Twitter at that point, and I sort of saw this message come by, which said that, speaking of languages, it's actually time to stop using C and C++ for any situation where we don't need a garbage-collected language. Instead, we should choose Rust. And that's not from anybody. This is the Chief Technical Officer of the Azure Cloud Computing Service run by Microsoft. In fact, he went even further and said that actually for the sake of security and reliability, C and C++ should essentially be deprecated for new projects. And we're going to look at why such people with such significance are saying things like this very shortly. In 2019, Microsoft released some research describing they had a look through all of the security vulnerabilities that Windows had faced. And about 70% of them were caused by one class of error called memory safety bugs. And Rust is a language which eliminates that entire class of problems at compile time. So it's impossible to create a memory safety issue in Rust, and you don't need to sacrifice speed. The NSA came out in the same year and said that memory safety is becoming very important for the United States government, and this has led to even more noise over the last couple of years. And the question might go, has Rust actually been able to demonstrate that it is successful? Well, Android released its first Rust code in version 12, and when they released version 13, they went back and had a look at how Rust was doing against its static analysis tools that it was applying to its C and C++ code. The historical average of a defect rate was about 1 error in every 1,000 lines of their C++. Android had released 1.5 million lines of code, subjected it to the same analysis, and it found no errors in the Rust code. So this is why Rust is becoming very significant for large companies, because they finally have a tool that provides the guarantees that they've always wanted, without needing to sacrifice the performance of a garbage-collected language. And we'll talk a little bit about what a garbage collector is, but now we are actually starting to see more pressure being applied to industry. And if you want to interact with the United States government now, you're going to have a story around memory safety. This is a very important part of the puzzle that you will need to be able to have an answer for when people in government start to ask, what are you doing to protect us against memory safety errors? So this is a press release from the White House, along with an associated paper, which basically said that if you want to contract with the US government, you need to be memory safe. So we need to actually start explaining what this is. There are many different definitions, and this is one that I think is most useful, especially if you're unfamiliar with the term, and that is when you put data in a variable and leave it there, and you come back later and you access it, it's still there. It seems like a very trivial problem. Unfortunately, the best programmers in the world are not able to guarantee for most programs that this is actually the case. in the face of concurrency and multiple CPUs and so forth. But we'll use this as our working definition of memory safety. Rust is the only language that exists at the moment that provides this guarantee without runtime overhead. And you can see why it's important for these very large businesses. But what I'm hopeful is that you are going to also see that there is a use for you, and you might be applying it into a much smaller business, or even your own hobby project. And the language itself is very nice to use. It's quite fun, actually. And yeah, so this is what the rest of it is about. And now I'm going to try and teach you Rust in about 20 minutes' time. Good luck. Bearing in mind that Rust also has this kind of horrible reputation of being very difficult to learn, let me show you why that is a problem as well, or at least show you some of the very difficult areas which we can fix. So here's the start of our program. All Rust programs have a main function, and we're initializing we're going to print we're going to do hello world, but just in a long form. So we're going to create an empty string, and then we're going to add to it, and then print it out. So we create there's Copenhagen, and we append to this empty string, and print line has this special syntax with an exclamation mark. It shows that we're using a macro, which is the way that Rust gets around from the fact that it's very particular about about type safety. And we want things like asking the Rust compiler to interpret those curly braces to replace the word out with the variable name. And to do things like that, you need to ask the compiler to do more than just call a function, which is why you see macros being used as well. Now, this actually generates a problem. And we can start to see already one of Rust's philosophies, and that is that data is always going to be safe by default. Your variables are immutable. If you want to be able to modify them, you need to ask for mutation. Now we get Copenhagen out, which is nice, and we start to get a good feel for how Rust works. We're always going to be biased towards the safe path. Now we'll add some changes. We want to print out hello Copenhagen. That's fine. But then we learn some more of the language. You might read some manuals or something and find this new macro called write. Write will send data to a network socket or to a file, but we're going to simulate a network socket with a string. And you can see here, so we have this kind of complicated syntax for an ampersand MUT, which asks for a mutable reference, otherwise known as a unique reference or a read-write reference to that string. And this creates a very strange problem for beginners. They find a piece of code that exists in a code example, they copy and paste it into the editor, and suddenly it doesn't work. The reason why this is that Rust is not an object-oriented programming language. It uses something called a trait, which if you've used Haskell, which fewer people have used than Rust, probably, this is a type class, and otherwise known as, you can sort of think of it as an interface from object-oriented languages or an abstract base class. We need to actually import the right trait into the local scope, and then we get access to its methods, which means that it will suddenly work with the right module. That's all of the Rust that we need for now. Well done. I'm now going to teach you about some of the fundamental concepts of the Rust language. So we've heard about a couple of them if you have been observing this language at all. Difficult things like ownership, lifetimes. What does it mean for something that is like dead to be alive? Doesn't make sense. And borrowing. This also just feels like a very mixed metaphor. And we're also going to be touching on Rust's error handling as well, because it provides a different approach than what is, let's say, orthodox currently. A value has an owner. We can think of this when we're starting out as the scope, like inside braces, where it is valid to access that value. We can move the ownership around different parts of the program, but there can only be one place at any given time where something can be the owner. This is a metaphor. There's no actual property register in like sort of the government of the Rust compiler that goes and checks. And the metaphor is quite stretched. So there is no, when we start talking about access and references, it's impossible to prevent another part of the program from accessing the value that you own. The responsibility of an owner is just related to deletion, essentially. We want one unique place where we can delete the data. A lifespan is conceptually a logical span of time when it is valid to access a variable. Most programming languages use two concepts when they are defining a variable. They assign a name and a data type. Rust has like a bonus third thing. A Rust variable also has a lifetime associated with it. The Rust compiler at compile time will check whether or not a lifetime, if you ask for the value, we define our out variable, and then later on in the program we go and ask for it again. Rust will check, has out been deleted? And if it has, your program will not compile. And essentially we use the verb to borrow to just mean take a reference to. Strictly speaking, this is implemented as a pointer, but we add some extra semantics around this that's associated with lifetimes, and so we add a new verb there as well. Let's see what this looks like in practice. I'm from New Zealand, and one of the things that I like to do, it's going to sound silly, is contribute to an open source map of observations of like natural life. And so where I live from Wellington, which is sort of in the middle, and there are a bunch of penguins there. So New Zealand has penguins, and let's just kind of sort of see what this looks like. So we're deriving debug. What does that mean? It means that I can be printed out. So I ask the compiler to write the methods for printing out the values. I'm creating an enum penguin. So the words there, hoiho, korora, and tāwaki, they're from the native language of New Zealand, te reo Māori. Hoiho is a little blue penguin. In Australia, they're called the fairy penguin. And so here's one here. So here's our sighting. And then I can print it out. And so we see hoiho. So this is the smallest penguin species in the world. They're very sweet. But they get hit by boats a lot. And anyway, let's go and change our code. So we want to illustrate borrowing and lifetimes and so forth. So here's our new code. We've introduced a new variable called new sighting. And we're printing that one out as well. And essentially, we've created a space for our penguin to move to. And so it shifts. In the Rust world, when you use assignment, you are shifting the ownership of the data to the new variable. Now, even though it exists in memory, we haven't changed anything, it is now illegal to access the original variable sighting. So any reasonable programming language, this would be perfectly valid code. But in Rust, we get this very angry compiler error message saying, borrow of moved value sighting. What? And I can explain what this means a little bit. So here is the playground, sort of the Rust, it's an online Rust interpreter, or compiler, sorry. And I want to sort of demonstrate what I mean by the fact that if I have a block, this block at the end of line 9 is where citing is allowed to be used, and I'll get a very similar error message saying we cannot find the value citing in scope. So even this assignment won't even work. I need to fix the bug. Does anyone have any suggestions for fixing the bug? Copy. That was the suggestion that the compiler suggested. Maybe there was a second penguin. So how do we do this? Well, one of the ways we can do this is by asking the compiler to write some methods for us. Well, I could do this manual if I want. And here's one way. So I derive clone, and then I say that my citing, which is actually a penguin, let's say, we clone it. And now we get a warning saying that these other two variants are not used. But there is our print statement where we see two hoi-ho, two little penguins have appeared in our program. We have been very explicit about the semantics that we want. We have asked the compiler to create a second copy of the data. However, that might not be what has happened in reality. It might be that we saw the same penguin twice. And so one way to think about that would be to take a reference or to, quote, borrow the original. We do this with an ampersand. The syntax is inherited from, say, C or C++. And this also works. The interesting thing about the data type is that this is another citing is typed differently than is not a penguin itself, but it's actually a reference to a penguin now. Okay. Lifetimes are a way of describing the fact that your variables need to actually be, so here's our borrow, and I can't sort of accidentally, I can't delete, let's say, oh no, this isn't quite working. Rust. This small example is a little bit too small, but we cannot create a situation where I could, let's say, like delete another citing, and then we can't ask the code, like the compile just won't work. There is a way to, we don't really have a delete method, but there's something similar. The Rust terminology is drop. Nope, we got a syntax error to fix. And the reason why this works is that, do you remember how I said that the data type is a reference? Well, Rust is trying to so I'm dropping the reference, but actually not touching the original citing. And when you ask the print line macro to print something out, what it will try and do is take a new reference. And so drop isn't quite doing exactly what I want, so I'll leave that there. And we can get another form of fix, which is that I can also ask Rust to implement the copy trait. By default, Rust will use move semantics, where we literally move the penguin from one variable to another. If I opt into copy semantics, then values will duplicate implicitly whenever there is a breach of Rust's rules. This is the opposite to how C++ works. Okay. Yes, I have explained things in the playground. Error handling. Rust uses values to represent errors rather than exceptions. That is, we've got some time just to kind of look and see what this means. So conceptually, I've made some changes to my code. I've refactored a little bit. And let's start down in main, down here in line 24. And I want to loop. So here is a loop. We're looping 10 times over some action where we make an observation. And our make observation function returns an enum that when you find or detect a value of any type t, you return the found something variant of the enum. Rust's enums are more powerful than named constants. They can actually contain values within them. Now, the syntax here looks kind of ugly. We've got these kind of little big, long words, but that will be fixed very shortly. Your code will, let's kind of work through this a little bit. I'm down on line 26. I've made my observation, and that variable is sort of a type that could be either of two things. It could either be something or it could be nothing. And if it is something, then record an observation. That's our job. Now, there are actually some bugs in this code. For example, you can see here that I have a pattern like I'm matching 1 twice. So this is an error that we really don't want to sort of infiltrate our code. If we have a match statement, we really want some help here. So I'm going to hit run, and the compiler is going to tell me to fix a few problems. First of all, it's saying that I have detected that one of these lines here, actually it's checking a different problem down the bottom. You can see here that, and I may be citing, I don't actually handle the nothing case. I try to leave it to just, and so what we need to do is be explicit with our intent. It's that if we find nothing, then we really don't want to do anything. There is some syntactic sugar for making this a little bit more comfortable. This is a very verbose style where we use an explicit match statement, but it demonstrates the principles of the way Rust is trying to operate. So we've fixed one problem, and now the Rust compiler is saying on line 15, you have got a pattern which will never match. So we go up on line 15, and here is our pattern, which we need to fix. And so we'll just add this to the number 2. So about 50% of the time, so we're rolling a dice between 0 and 6, or it's actually, 6 values, but it is the exclusive range unless we ask for an inclusive range. So about 50% of the time we find nothing when we go and look for penguins. Otherwise, we will find one of these 3 species. And now we are close to fixing this thing. Oh, he says, we get another problem. And that is that our record observation function hasn't been implemented. Rust provides the ability for you to kind of create some scratch space with a to-do macro, which will satisfy the type system. We are going to fix that soon. For now, I'm just going to print out the penguin. Penguin doesn't implement display. Okay, so I need to opt in. So I've got derived debug. The printing to text takes 2 paths. One, I can use display, which is intended for end users. Or I use debug, which and to invoke the debug output, I have this kind of question mark modifier on the macro itself. And you can see here that we have some instances of korora and tawaki penguins. Even though in reality they don't live in the same place. It's okay. I thought that people wouldn't mind. Now, the first thing to fix, or at least the way that we link this back to error handling, we've got some code that works, and you can see that we've manually created a type which can represent two paths. Rust's standard library does this itself. We don't need an observation attempt. Instead, we return option. Option is very similar to Java's optional. A lot of languages have sort of are moving towards something like this. Now, and so this all changes, or it gets significantly shorter. The interesting thing here is that option is, in some sense, stronger than Java's optional, because it is impossible to create a program where you could have a null pointer exception. They do not exist in Rust, and you just cannot generate them. And you can also never accidentally forget to handle a case. The Rust compiler will just, so this, our code down the bottom needs to change as well. So some penguin, if we've got nothing, then we do nothing. So here are our two penguins, and we didn't find many penguins in our 10 observations that time. It's interesting to me that we are having a kind of a strange bias. So FastRand is a third-party crate. A crate is a dependency. This playground has about 100 of the top dependencies that are used in the open source world. And U32 is asking for an unsigned integer that is 4 bytes or 32 bits wide. From a control flow point of view, I don't have a return statement. This also illustrates one of Rust's philosophies, or the where Rust comes from, or its heritage. Rust is essentially, I like to call Rust a functional programming language in disguise. And so what's actually happening is Rust will return at line 19 some sort of observation which is returned from match. Now, interestingly, the way that Rust works is that every block will return the value of its last expression. And so functions are just blocks that contain multiple inner blocks. And so we actually don't need a return keyword. And everything in Rust is an expression, including if and else, for example. So we've talked a little bit about option and about the way that control flow works. I now want to talk about a different enum, which is defined in the standard library, which is errors. Errors in Rust look a lot like this. I'm going to use a different word so that I don't collide with the original one, but let's call this outcome. And outcome on one half might look like success, and it might look like failure, but we need to parameterize a success type by some type t. And also the failure, let's call that an f. So we now have 2 type parameters. And our record observation, we could say that we have some sort of outcome. And I'm going to say successfully, if we're successful, we just print out what is known as the empty tuple or the unit type. So just to indicate OK. And outcome success. And otherwise, we have some error message. And I'll just use a string. And this would allow me to describe the fact that, I don't know, my equipment failed, so I wasn't able to record the observation properly. Now, this is exactly the way that the results type in the Rust standard library is defined. And it's literally this long, except it has a couple of extra annotations. One of them is we give the compiler an instruction that anytime that there is an outcome or a result, you must use it, which will trigger a compile warning if you forget. Okay. That is probably 80 or 90% of Rust. If you can grasp error handling, if you can grasp the concept of a single unique owner, and the ability to borrow or refer into that owner, and then make sure that references to values have a specific lifetime, then you've basically got Rust. There are some other things about the fact that its control flow is a bit strange, but that's okay. You'll learn that with practice. It will act. Now I find it a little bit hard because I'm sort of immune to the problem of newer programmers or new people learning Rust looking like, this is very strange. Okay. I now want to talk, though, about why Rust is as fast as it is, because this is a very significant and really important part of the story when you go and try to advocate for more Rust at work. There is no garbage collector. It is what these are my views, by the way. It is, so I call it stack heavy. I'll explain what that means pretty soon. And also, we have these very high-level constructs which kind of actually use almost no memory or no execution time at all. What do I mean by a garbage collector? Well, what I mean is that Rust doesn't add on an extra part of your program that's running alongside it. This has a really important benefit in that there are no latency spikes. So here are a couple of stories. This is related to memory use. An example from Tencent. They had a reverse proxy which was written in Node.js, and they had like 800 CPUs. And they removed, this was the log where they removed, I think 700 of those CPUs while reducing their memory footprint by something like 90%. And significantly, they also, you notice how much flatter the line is. It's much more deterministic. Rust has deterministic deletion. There isn't the ability, you don't have a garbage collector that holds on to values in memory and the heap just grows and grows and grows and grows. That issue doesn't exist in Rust. This one is more significant. This is Discord's discussion about why they moved from Go to Rust. The purple lines represent the old system written in Go. And you'll notice that every 2 seconds, there was a latency spike. This meant that messages were being delayed, and this is while the garbage collector asked the whole runtime to stop while it freed up memory. The Rust is relatively difficult to see, but it is the blue line, which is both faster across all cases, as well as never incurring that garbage collection overhead. And the determinism of the entire system is improved. And so stories like this is one of the reasons why Rust is becoming useful, not just for the fact that it can be seen as memory safe, but also your users benefit too, and so does your operations team, because suddenly your service is significantly more stable. I call Rust stack heavy. That is, it will allocate objects on, I say the term object, I just mean value, on the stack whenever it can. This has benefits because using the stack over the heap means that there is less bookkeeping when you go and ask for the value again later. It's almost the inversion of the way that other programming languages use. Something like C++ or, C# or Java will use the heap first, except where they have primitive values which will live on the stack. Here's a very small diagram of their memory address space. Conceptually, you could think of memory having three areas. We have a stack, which is fast, and there are specialized instructions inside your CPU to move from one location in RAM to another. We update it's a register in the CPU called the stack pointer, and that's like less than a nanosecond. It's like one cycle. The heap, to update the heap, we need to go back and find the location in memory, maybe bring in that page, but it's extremely flexible. One of the problems about the stack is that you need to know exactly how wide it is because there's no ability to dynamically change values at runtime. There's also a sort of a third space which people don't talk about as much, and that's the location where global variables live. Rust has a bit of a problem when you start to learn it in that there are two different data types for representing text. In fact, there's like 17, but we don't worry about that. And the reason was Rust is extremely precise. And one of the things that it does is have the string literal data type is different than a string with a capital S, because the string literals, the data lives in this global space, known as the data segment in the address space, if you're ever interested in those kinds of things. Whereas string with a capital S, its data lives on the heap. Rust values precision, it values safety, and so it makes a big distinction between those two. And we've seen before that with the use of kind of this, I want to talk a little bit about one of the other properties of string is that its content is guaranteed by it to be UTF-8 encoded. And yet there is no runtime cost associated with checking. That's pretty cool. And it's because all of the initial, the type system itself, or has everything that operates with a string knows that it's UTF-8 encoded, and you cannot construct a string type with invalid data. There's sort of no API that would allow you to do that unless you really want to go and use raw pointers, in which case you will get a very significant, we use an unsafe block, which is exactly what it says. An unsafe block has the significant, the unsafe block's function is to push responsibility to you as a programmer. For example, we talked about null pointers, or at least in Rust not having null pointers, but here is an integer which I then put on the heap, and then I take an option to, so it might be missing. Like, it might not be there. And the thing that I want to point out is option essentially is doing the same thing as a nullable pointer. But it doesn't use any bytes at all in RAM. It's invisible in the disassembled code because it actually makes use of a property for the fact that pointers in Rust, references are always valid, therefore the null pointer doesn't exist, and therefore the optimizer can use the 0-bit pattern, like the null pointer, to represent option. So it's kind of cunning in that way. As I wrap up, I thought I'd talk a little bit about who I am. My name is Tim. I have written this book. If you are interested in Rust as a non-systems programmer, trying to understand what systems programming is. I also run a training business and consultancy. This has been an absolute pleasure, and I've got about 3 minutes per question.